Well, good morning or good afternoon, depending on where you are at. My name is Atarod Azizi Namini, Director of the ABC UTC at Florida International University. A couple of quick news on upcoming 2022 International ABC Conference. As we have mentioned, it's fully in person, no hybrid. If you plan to attend, please register. You can go to our website and register online. I'm also delighted to let you know that using the travel scholarship alone, we were able to support travel of about 70 bridge owners, state DOT, the employees to attend the conference. In addition to that, some state DOTs actually have supported the travel of their own staff using their own resources. So to date, we have more than almost, I would say, 100 bridge owners that have registered to attend. We are expecting the conference to be in the order of the 500 or 600 attendees this time. So about 100 of them, more than that, still there's a time to registration. More than 100 of them will be the bridge owners. Also, for those of you who are interested to get a continuing education, we will give a certificate stating that you have attended a continuing educational conference. But it will be your responsibility to show it to your board of professional engineers to get the credit. Also, just to note that the FIU is a sponsor of continuing education in Florida and New York. Day before the conference, on Wednesday, December 7, we will have several workshops, in fact, 4 workshops. 3 of them are related to design of the steel, pre-stressed concrete, and FRP composite bridges. The steel bridge design workshop and the pre-stressed concrete bridge design workshop are really covering the basics of the designing the steel and pre-stressed concrete based on the AASHTO LRFT bridge design specification. It's not just the ABC. It's just so those of you who are interested to refresh your basically the design and so on. This will be a very good workshop for you. As an example, the pre-stressed concrete bridge design workshop it's got four different sections really. The analysis and design, Dr. Bijan Khalegi will be covering in a very detail the AASHTO LRFT bridge design specification related to the pre-stressed concrete design. We will have William Neckes covering the fabrication of the pre-stressed concrete bridge. Greg Freeby is going to be discussing the for segmental bridge design and construction, and then there will be also a module on available analysis tools. So far, we have about 40 exhibitors in the conference, but there's a space, so it's a very good opportunity to showcase your products, your services to the bridge owners and the consultants and the attendees. So if you are thinking about the exhibiting, there's still booths available for exhibit. You can go to our website and reserve your booths. And we hope to see many of you in December in Miami, Florida. The conference is going to be held at the Hyatt Regency Hotel.
Our presentation today features the Alaska Department of Transportation and Public Facilities use of ABC to address climate change on behalf of a remote village north of the Arctic Circle. We'd like to thank Rich Pratt, former Chief Bridge Engineer with the Alaska DOT&PF, for coordinating this presentation. We're pleased to welcome our presenters, Elmer Marx, Acting Chief Bridge Engineer with the Alaska DOT&PF, and Nicholas Murray, Bridge Engineer also with the Alaska DOT&PF. Would like to also introduce our Q&A session moderators, Paul Lyles, formerly Georgia State Bridge Engineer, and Don Diggeman, current Georgia State Bridge Engineer. We'll now begin our featured presentation. Elmer?
Thank you, Mary Lou, and welcome everyone from across the nation. You have to admit, it's pretty cool that Atarod is in Miami and Nick and I are here in Juneau, Alaska, the other side of the country. So modern technology at work. So thanks for that. Before I start, I want to thank and maybe inform you that Rich Pratt, the Chief Bridge Engineer for Alaska DOT for over 20 years, has retired as of last month. In addition to being our Chief Bridge Engineer and leader here with the Alaska DOT, Rich was the chair of the AASHTO T3 Seismic Committee for 17 years, during which time we developed the seismic guide specifications, the performance-based seismic design for highway bridges. We updated the isolation manual. He really had a lot of achievements both here at the state level and at the national level, and was really the force behind getting this webinar arranged for Alaska DOT and FIU ABC. So thanks to Rich and congratulations. I'll start today by speaking sort of globally about Alaska's use of ABC. The map that you see on the screen, that's Alaska. Each of those yellow dots is one of our bridges. You can see that in the center of the state, a lot of the yellow dots are connected. Of course, those are along the road system. But many of the dots west in the western half of the state, those isolated dots, those are off the road system. These are remote parts of the state that have villages, some of them subsistence villages, without much road system. Maybe just a little bit around their community to get from their village to the dump or to an airstrip. But for the most part, there's just a handful of bridges with road access. Consequently, Alaska has sort of been using ABC since before it was called ABC, before it was cool like it is now. The reason for that is, again, these remote locations are difficult to access. Many of them, again, have no road access, so we either need to fly in the pieces or barge in the pieces or use ice roads in the winter to transport in the pieces. That's pretty challenging. Further, our winter months are pretty long. In Alaska, they say our seasons are almost winter, winter, still winter, and construction. So that doesn't leave us much time to work. We don't have a lot of warm weather. Plus, in Alaska, the daylight hours get very short in the winter months, and they get much longer in the winter months. So oftentimes our construction season is limited to between 3 and 5 months to get a bridge built, and we prefer to have our bridges built in that single construction season. So one of the most popular superstructure types that we use in Alaska is the decked bulb T. We've been using that structure type since about 1973, and it represents a pretty large part of our inventory at this time. That is, our deck bulb T girder bridges are used throughout the state. For us, they are the low-cost solution. If you can get a deck bulb T to work at your site, if it meets the geometric requirements and so forth, it will almost certainly be the least expensive option. We have 2 fabricators in the state and several fabricators outside the state that make these systems. We're very pleased with them. They go in very quickly. As you can see in the photo here, they're pre-decked, so there's some welded shear tabs and a grouted keyway, then a minimal amount of cast in place work. And in short order, generally speaking, one construction season will go from clearing and grubbing all the way through striping and opening to traffic. For our substructure, a very common system for us are concrete-filled steel pipe pile extension bents. That's quite a mouthful, but they're just concrete-filled steel pipes that support a cast-in-place or mostly cast-in-place concrete cap beam that in turn supports pre-stressed girders or structural steel girders or other superstructure types. These are galvanized steel pipes. They're galvanized from the top of the pipe to 10 feet below the final ground line. That's to address corrosion. Once you get about 10 feet below that final ground line, there's a lack of oxygen, so corrosion is pretty much cut off. It eliminates our need for cofferdams. That's a really big issue for 2 reasons. One is that's a time commitment and a cost commitment to build a cofferdam, but the other is resource agency permitting issues. We have fish windows, like I'm sure most of you are aware of, that limit the time that we can do things like pile driving or really any in-water work, including riprap placement. Additionally, those concrete-filled pipes act as stay-in-place permanent forms. We include the steel shell and the reinforced concrete core in the entire cross-section. That's to say, we're taking advantage of both the steel shell and the concrete as a hybrid composite system. These systems work very well for us in our high seismic environment where liquefaction and scour are not uncommon. It's a high-strength system, which oftentimes is associated with lower ductility, but this is also a high ductility system. Consequently, it has a large elastic and plastic deformation capacity. Very important characteristics for us here in Alaska, where, again, earthquakes aren't uncommon. Most recently, the 2018 earthquake near Anchorage perhaps 8 miles or so outside of town. I think it was a 7.2 magnitude event. Really had no significant bridge damage. There was some cracking of shear keys and expected kind of, let's call it service level events, but the system seems to be performing very well. We've done a lot of testing. We have strain limits for deformation capabilities, calculations, and so forth. So it's a pretty common system for us. So those are our sort of big picture issues. Like I mentioned, about 41% of our bridges in the state are these deck bulb T-type systems. Since the 90s, about 60% of all new bridges are deck bulb T-girder bridges. So again, I think that classifies us as ABC. Of the bridge types that we're going to be speaking about today, steel girders with a full depth precast concrete deck panel, about 3.5%, not too many, but it's a growing number and the system's working well for us. We're pleased with their performance, the speed at which they can be built and so forth. And again, these are mostly built off the road system. So the bridge that Nick is going to talk to you about next has no road access. So you can fly in a small plane. It doesn't have like a 747 capability or anything like that. Or you can barge in, barging out of Nome, the most close community. So with that, I'll introduce Nick Murray. He's an engineer with us here at the Alaska DOT Bridge Office. He's been with us over 10 years, I think maybe 11 or 12 even, and it's done a lot of our more challenging work. So with that, Nick, it's over to you.
Thanks, Elmer. So Mary Lou suggested I add a slide in to show where Alaska is, because unlike all the maps show, we are not in the Pacific Ocean next to Hawaii. We're actually pretty far north. And so if I zoom in on that to where our project is, you know, every presentation I have to start with where the project is. So Elmer and I are down here in the southeast portion of the state, down here in Juneau. That's the state capital, and that's where DOT is headquartered. Kivalina, where I'm going to be talking about today, is very far north on the western coast of Alaska. There's only a population of approximately 444 people, roughly. That line that just appeared on the screen is the Arctic Circle. So Kivalina is about 80 miles north of it, and the Arctic Circle defines the point at which, you know, one day of the year the sun never goes below the horizon, and then conversely in the winter the sun never comes above the horizon. So land of the midnight sun, very long, you know, daylight hours in the summer, very dark winters, I'll say. Because it's on the ocean, the temperatures are not quite as extreme as you'd expect. It's kind of regulated by that. That being said, there are still very low lows, but in general, you know, it kind of hovers right around or just below freezing. And then something else to point out is that this area has been inhabited for, you know, 1,500 years or so. So I'm going to speak quite a bit here about what the point of this project is and why it's important, and that'll come back into context. So there's one more point of comparison. Juneau, where we're sitting today, is about 1,100 miles away from that bridge location. So to be in the same state and 1,100 miles away, so is a point of comparison. If I take that same 1,100 miles, for those of you sitting in Miami today, that'd be the same as going to Texas. So anytime I get to point out that Texas is not nearly as big as they think they are, it's always an advantage for Alaska to point out that we're over twice as big as them. So like Elmer said, this is a picture of Kivalina. You can see that little gravel runway, pretty small. The Chukchi Sea, which is part of the Arctic Ocean, is to the left, and you can see some floating pieces of sea ice in there. And so Kivalina is actually on, you know, a remnant of a sandbar essentially. So it's freshwater lagoon on the right of your screen, and then a saltwater ocean on the left. So if I zoom in a little more, this is the entirety of the town. You know, there's no suburbs to this is it. So every person you see lives in town, and you can kind of get a sneak peek of where this is going. If you look around here, this entire southern east portion of the island is armored. That was a U.S. Army Corps project that went on in early 2010s. So why is a bridge needed, and where is a bridge going? So the villages that are up in this part of the area, they're protected by the sea ice. I know that seems kind of counterintuitive, but the sea ice provides a big damper to any storms that come in from the Arctic Ocean and the Western Pacific, so tsunamis in particular. And as sea levels have risen and temperatures have increased, that sea ice is becoming less and less reliable. It's showing up, you know, later in the year. It's dispersing earlier in the year, and so even compared to a few decades ago, that sea ice is not providing the buffer that traditionally had been there. And so you see on this picture here, you say, oh, that's a lot of sea ice, and this is in June. So, traditionally there would only be open ocean for maybe 2 months of the year that Kivalina was actually exposed to open ocean, and the rest of the time it's protected by it. So if I take one step further back, what you'll see is that I'm pointing out it's not just a little bit of sea ice. There's approximately 50 to 100 miles of sea ice between open ocean and the village. So that gives you some sense of just how much protection that is. When it freezes 10, 15 feet thick, it's acting essentially like another landmass protecting the village. And then one other thing I'll point out is that these two islands down here, that's the Diomede Islands. So yes, you can see Russia from parts of the US. So there's a video that's going to play next. I don't believe we got the audio to work, so I'll kind of speak over a little bit. This basically points out that large portions of the beach have been lost in the recent years. You can see there's no trees in the area. And so that sea ice you can see is broken up and not as firm as it would have been. Kind of a unique fact is that about 8 years ago, President Obama became the first sitting president to visit the Arctic, and he actually flew over the village of Kivalina in Air Force One. It's kind of a big deal for a village of only 450 some odd people. And he pledged $2 million to support voluntary relocation efforts. And that's the former governor he's speaking with right there. They estimate, though, that it's approximately we'll need about 100 times that much to relocate these villages. So 2007, there was another big storm that came through, and you can see they're trying to quickly armor it. And because the village is so low-lying, half the community ended up having to evacuate. So the young children and the elders were able to fly out, but a lot of the other people just had to take small boats across to the mainland. And if you look back at those pictures I showed earlier, there's not a town on the other side, so they're just kind of going to open land. And it's a big part of cultural identity, is that this area has been inhabited for a very long time, and this village in particular has been inhabited for over 100 years before Alaska was even a state. And so the cultural identity of the community is very much tied to this location and a subsistence living. So she had mentioned, there have been pushes to essentially make these people move to other villages, but it comes with a huge cultural and societal cost. So where is the bridge going, and I guess what is the project in general? So Kivalina is down here on the west, and you can see this kind of raised area of land over here. You can kind of tell it looks a little different. Is essentially the next highest ground. Like I mentioned, there's no trees. This is all just low-lying tundra. And so the project was to build a 8-mile gravel road to get to that area that included crossing this lagoon. So it's about a 3,200 feet causeway with a 190-foot single-span bridge, which is what we'll be talking about today. So the delivery method for this project was chosen as a CMGC project, or Construction Manager General Contractor. The reason why we went with that, I'll speak to in a minute, but we issued an RFP as DOT the owner, and selected a contractor being brought on board prior to the design being finalized. Something a little bit unique about us is that DOT internally still performed the majority of the roadway design work, and we performed all the bridge design work. There were some specialty consultants brought in to do coastal engineering and those sorts of things, but we did the majority of the design work in-house. And then important to us is that the contractor was able to look at those, partial design plans and give us feedback on, optimum ways they thought they could build something, or if they thought something was going to be better, faster, cheaper, we could incorporate that prior to it going out to construction, or if they saw potential risk in items. So we've been using CMGC for, I want to say, maybe the last 7 or 8 years now. We've had a positive experience with it. It allows us to collaborate with the contractor, but it still allows for them to propose, new ideas and efficiencies. But at the same time, as the owner, it allows us the opportunity to steer those decisions as the long-term owner. And for us, it just provides more control to the owner than a design build project where it sort of becomes a hands-off and you let everything go. And like I mentioned, it provides for the contractors construction methods and special details they want. So for this project in particular, an example is they wanted to be able to drive their unloaded off-road dump trucks across the bridge. Not something we would have normally evaluated, but during the design process, we said, sure, we can look at those trucks and make sure that the bridge can handle those, loads that are not described by AASHTO. And then one of the more important things I think is overlooked is that since the contractor is brought on before the project goes to construction, if there's a disagreement or negotiations fail on the guaranteed maximum price, we can still turn around and issue that project as a regular design build bid at that point essentially, and bring on another contractor through traditional contracting means. So that gives us quite a bit of flexibility up until that point. So quickly just want to highlight the main contractors and suppliers and fabricators and those sorts of things on this project. You'll see a couple of them have taken it upon themselves to write up some little articles about this project, being that it was so unique. So I left a couple links in there if you want to look at it. So why are we using ABC on this project? A lot of times, states or projects, they'll say, well, the impact to traffic is just too great. We need to have a really quick project. I think the project highlighted last month's webinar had an ADT of 220,000 or something, just astronomical. You could probably guess from us, the picture on that map, that our ADT is not quite 220,000. In fact, it's about 18. And since it's a one-way bridge that doesn't really go anywhere, it's really about 9 trips total. So not really an impact for us. The reduced construction time, this project occurred sort of in the middle of the first year of COVID and all sorts of other issues that came with that. So it still became a 2-year project. That includes the entire road, obviously. So building 8 miles of road from scratch. We've estimated that, sort of based on what we looked at, if the bridge was built in one straight shot, it would have roughly been about 3 months to build the bridge. But the bridge was not a necessarily critical path item for the project as a whole, and so they kind of started and stopped to move to other things. So the real reason we used ABC is that it's such a remote location. So getting equipment, laborers, materials to the site is just a logistical nightmare. And a lot of times, equipment that goes to that site will be mobilized once and brought back, when the entire project is done. So minimizing the duration of construction time is important to minimize some of those mobilization and demobilization costs. The other thing that we try and do with our style of ABC is to minimize specialized details or equipment. So, post-tensioning is a good example that for most states may seem routine, but it's a pretty specialized in the end for us and requires some specialized equipment. So avoiding details like that can't be done with regular general contractors is important, because it just increases the cost, increases the likelihood of scheduling issues and those sorts of things. Cast in place concrete is exceedingly expensive. Obviously there's no batch plant in town, so all of the aggregates and cements and those sorts of things have to be brought in to site and mixed. And then because it's being mixed in a temporary batch plant, quality control can sometimes be a little iffy. And so we want to maximize our use of precast elements. Additionally, because it's such a remote location, future maintenance will likely be very limited, or more or less negligible. And so we want to avoid any details that are what we see as typically maintenance prone details. So joints, drains, bearings, those sorts of things. So any of those we can eliminate will help the bridge maintain a longer life. And then finally, as Elmer mentioned, weather and daylight considerations can drive the schedule, especially in Alaska, where you have a short working window. And with all that sea ice, there's only certain times a year you can bring equipment in and out of the site. And so it really drives the schedule. So in terms of the actual bridge, first start of any project is we had to go do foundation drilling. This occurred in April of 2018. We mobilized a small drill rig up there, a contractor, I should say. So kind of unique is that, they have to access the site using snow machines. And what's interesting goes back to, climate change and thawing ground conditions up here, is that when there's frozen ground, it looks like really great soil. You get great end bearing resistance. And so we have a fair number of bridges that were supported on frozen ground with very short piles. You drive a pile and you essentially get infinite bearing capacity on ice. But once that ground begins to thaw, your piles start to sink. So this is a picture of a bridge down in Nome, so just a little bit south of this project. And this is supported on piles. This isn't a spread footing that's sinking. And so if you go back to the original pile driving logs from the 80s, they were only driven to a shallow elevation. You can see we're right at the ocean. So, those piles are probably only 30 feet long or so. And, one corner of the bridge has now settled 2.5 feet. And that's, true pile settlement. And like all settlement, if it had all happened uniformly, it probably wouldn't be that big a deal, but it never seems to happen that way. One side's going to, settle more than the other and starts to tear the bridge apart. So an important part of our foundation investigation is to actually measure those ground temperatures over a period of time. So they installed thermistors along the boreholes. So this red line represents, 32 degrees, the standard freezing point. And so anything to the right of that line indicates that that ground is thawed. Anything to the left of that line indicates the ground is still frozen. But a mitigating factor at this site is because it's not really fresh water, it's mixed with salt water. Salt water freezes at a lower temperature. And so that apparent thawed condition is quite a bit more than you would initially think of. And then just a few other facts I kind of touched on real quick is that SPT testing in frozen soil, not particularly helpful because that soil is going to give you such high N values that it doesn't really provide a whole lot of useful information. And so what you have to do is predict what the thawed condition of that soil will be in 30, 40, 50 years. But, just like scour, if we assume there's gonna be 15 feet of scour, we have to overdrive our piles. Those piles have to be installed when the ground is currently frozen. So, kind of creates a catch-22 there. So the foundations for this bridge are 2 foot by 1/2 inch wall. They're approximately 80 feet deep, close-ended steel pipe piles. It's the same detail that Elmer showed in the intro where they're filled with a reinforced concrete core down to a certain depth. And then there's a gap region at the top where that steel shell stops, and that essentially allows us to dictate where that plastic hinge is going to form during a design level event. The piles were installed at the tail end of winter. As you can see at the bottom is about 4 degrees when they were doing this, but because the ground is frozen and the water is frozen, you have very easy access. A temporary causeway can be built right over the water. Large heavy equipment can be supported in areas that would normally not be able to support that during the spring months. So it's kind of worked out in our benefit to do some of that work in the winter. So as I mentioned from the foundation engineering report, we're essentially going to assume that that ground will thaw over the life of the bridge, based on climate models and those sorts of things, and just an uncertainty of how fast things are changing. So, but again, to get through that frozen ground, we essentially dictated that the contractor pre-drill through 3/4 to 90% of that final pile diameter down roughly to tip, and then they could advance the piles through those loose cuttings. So once the piles are in place, we need to do some abutment cap beams. We did allow precast pile cap beams as part of the contract, if they followed that NCHRP report 681 that's highlighted on the screen there. The contractor elected to use cast in place cap beams anyway. There was already cast in place concrete on the project, and there's some risks tied with that precast cap beams for alignment and getting things shipped up there in particular. And so on the bottom right, you'll see a picture of the cap beams were being cast in March, so still very cold. So they're obviously in heated enclosures, and Alaska, as part of our contract, requires cold weather protection whenever the air temperature is less than 40 degrees. And then ironically, the hard part is sometimes getting that maximum temperature to less than 90, and it's really easy to accidentally cook the concrete. So the cast in place concrete for this project came pre-assembled in super sack. So there was a pre-mixed package of coarse and fine aggregate and a pre-mixed package of cement, and then it was literally mixed in the back of a standard 10-yard mixer. And then on the right is, during one of the concrete curing periods, there was sort of an unexpected windstorm that came up and starts blowing around the enclosure. And so they're actually using the arm on this telehandler to sort of keep the tent in place. So the superstructure for this bridge are steel plate girders. The total length is about 186 feet. There are 2 field splices in each one. And again, that's just to minimize the shipping. So that longest segment you're seeing on the screen is about 104 feet, and then the others I think are roughly 40. The shear connectors, you can see, were shop welded to avoid field welding. Again, it's not a super specialty item to be field welding, but anything we can do to minimize QA, QC, and preheats and anything like that we can do in the shop, the better. The girders all ended up being spray metallized. Obviously, it's not in this picture. It was on its way to the spray metallizer. And these came out of Oregon. So pretty much all of our steel fabricating comes from down south. And then there was a total of 9 inches of camber along the total length. And these girders are roughly 6 foot 9 inches, just parallel flange. So how do you get girders from Oregon all the way up to Kivalina? So first they take a truck to the port of Seattle and they're placed on a barge. They follow up the coast of British Columbia through Alaska towards Anchorage. They have to go all the way around Unalaska, which is where Dutch Harbor is, if anybody watches Deadliest Catch or anything like that. And then like Elmer mentioned, they make it to Nome where they're offloaded and put on a landing craft. So in total, there's about 3,000 miles of barge transport just to get those girders up here. So, pretty important that they have a durable coating, because oftentimes what we'll find is, when something's been painted or hot dipped galvanized, sitting 3,000 miles on open ocean, by the time it gets to the site, it looks like it's already 20 years old. So if you notice from the pictures in the intro of the village itself, there's obviously no dock facilities. And so the girders themselves were loaded onto a landing craft for the last 300-mile leg of that journey. And you can see from this picture that, that's not all the portions of the girder, so it required multiple, 600-mile round trips. And then once they reached the village, you essentially just beached that landing craft and a temporary row was built and the girders were hauled directly off of there. The girders were put in place with a crane-assisted launch, so they were fully assembled and spliced on the ground and then launched on an alignment adjacent to the bridge. So you can see the substructures are sitting here. So instead of being launched over the top, they were launched off to the side and then was picked up by a crane on each side and set into place. And this went pretty smoothly. I think they got all of these set in a day or two. Probably the biggest ABC component of our project is our precast full depth deck panels. So they're the entire width of the bridge. So in this case, 27'4". They're relatively narrow in width. That's partially to keep the weight down and also to allow them to be shipped economically. So I'll point out a couple details. So there's blockouts for the shear connectors that'll line up with the shear connectors on the girders, obviously. So this assembles like a big Lego set, and all those voids will be grouted back after the fact. And then above each of the girders, there's 2 sets of leveling screws that'll allow the haunch to be varied to make it for camber or create a nice smooth riding surface. There's 4 sets of lifting points that the contractor is going to use to lift or bunk those with either a crane or a forklift or those sorts of things. And then because it's their full depth, that crown of the roadway is actually cast in. So there's no cast in place topping that goes above this. The deck becomes the riding surface. And as such, there's a little bit extra clear cover on the top since there's going to be no future wearing surface. So we discount a portion of that for sacrificial. The keyway joints are very simple. There's no longitudinal or transverse post tensioning. It's not a UHPC. It's just a standard 9,000 PSI prepackaged grout. And then here's a quick little detail. Those leveling screws that will allow that haunch to be adjusted as it needs go. So couple pictures of the deck installation. You can see, you sort of just work from one end to the other and you place grout in this void, for instance, and once it starts coming up in this void, you just start working your way down. This is the backer rods to keep that haunch in place, and these are the top of the leveling screws. So usually what you'll see is they'll put all of these in place, and then once the deflections have been accounted for because of that deck weight, they can come through and sort of level everything up and create a nice smooth riding surface. And as they start grouting from one end to the other, this contractor had a pretty slick little setup where it was a more or less self-contained grouting station that was moved down the bridge by a crane. And this is a fairly labor-intensive process. It's probably the most labor-intensive process of the bridge construction. But you can see they're rotting it into the joints and filling it as they go. And then on the right, they'll, once there's initial set on that grout, they'll come and match the roughened surface. So this picture of them fully assembled and placed but not grouted. And some of the big benefits we see about deck panel installation is this goes extremely quick, because it's just all the panels are identical. The only difference between the panels is some have rail post anchors and some don't. And other than that, they're identical. You can spin them 180. There's no directionality to it, so it's pretty quick to get those in. Because they're produced in a precast yard, these ones, for instance, were made down in Washington. You can achieve much tighter tolerances and much more repeatability, generally a higher strength concrete. And so, alleviates a lot of the issues with cast in place concrete. And then while they are still heavy, the nice thing about these is they're narrow enough that they'll still fit on the back of a regular truck. They'll still fit into a regular shipping container footprint. And so in that regard, they're they're a little heavy, but they're still easy to move around. And then because of the girder adjustment leveling screws I mentioned, you can account for varying camber, or if your girders don't come out exactly the same, you can fix everything. And then a big thing for us is that there's no access from below required generally. The leveling can be done from the top, all the grouting can be done from the top, so eliminates the need for false work or scaffolding or any access from below. Generally, you can do all this work from the top. So the end diaphragms for this bridge, once all the deck panels are in place, we were able to go with a jointless bridge, so there's not an expansion joint at the end. The expansion takes place between the approach fill and the end diaphragm, which is locked into the girders. And because we're able to do that, there's no exposed sole plates or bearings or anything like that. So these use a traditional reinforced elastomeric bearing pad that's hidden under this girder, and the rest of it, this is the free end, so allowed for expansion, contraction, and rotation, is all foam. And so once that's all done, you end up with this nice, clean looking lines. There's no cap beam to start accumulating dirt or moisture, and there's no exposed anchor plates or anchor bolts to cause corrosion and joint failure. So it's a pretty slick detail. So just a few finished pictures of the bridge. I like this one because it just shows how flat the adjacent area is. So you can see how that just a little bit of sea level rise or a little bit of storm surge can cause this entire area to be inundated. And the bridge is actually, at a higher elevation than the village. And so, making sure people have access to higher ground during events of large storms, was sort of the big driver of this project, obviously. And then a nice finished elevation, and we're pretty happy with how this bridge turned out for being in such a remote location. So real quickly, I'll just throw out some of the materials that we used. I've mentioned some of them. So the cast in place concrete was just a regular Class A 4000. The deck panels were a little bit higher, 5,000 PSI. Structural steel, we use predominantly A709 grade 50 T3. That T3 represents a Sharpie test at a temperature zone of 3, which I think is -10 degrees, 50,000 PSI. The structural steel piling is A709 grade 50 T3 again, or it's API 5L X52 PSL2. This is American Petroleum Institute, so essentially oil pipeline pipe. And then, like I mentioned, the grout is just a standard 9,000 PSI prepackaged. So the big question that everyone wants to ask is, this looks really cool, but how expensive is it? So I'm going to kind of go through some of the costs. Because it was a CMGC, there's not true bid prices to compare. But we have some information. We've done other projects like this. So I'll first show what we'd expect normally on an urban project, say sort of in Anchorage or Fairbanks, and then what this project was to give you guys a flavor of it. So traditionally, we're looking at somewhere on the order of $1,500 a cubic yard for cast in place Class A concrete. This project roughly came in at, I think, $6,000 a cubic yard, so about a factor of 4. So minimizing the amount of concrete is obviously important. Reinforcing steels, same sort of deal, about a factor of 4. Structural steel, not quite as much, more expensive. Some of this is tied up in the MOB, demob costs down below. But it also that structural steel prices have been so fluctuating lately that it's hard to find, a common number to compare. And that's the same thing with the pile. We've had local pile costs go up quite a bit as well. Pile driving costs on the order of 3 times as much. And a lot of that has to do with that pre-drill and frozen soil and those sorts of things. Those deck panels, we're typically only using them in remote locations, so we don't have a great urban comparison, but on this project, each of those are about $20,000 a piece. Class 3 riprap, about double. You can probably tell from some of those photos, there's not great rock sources, and so most of the riprap, if not all of it, is brought in on a barge from some other location, and so the transportation costs become quite a bit. Worker meals and lodging for this project, like $2.7 million. They're essentially building a small town for all of the contractors and the subcontractors, including, a camp and showers and bunk beds and recreation and all those sorts of things. And the mobilization was about $3 million. So, and then a couple lessons learned that we came out of this project. We really like the CMGC process that allows us to have a good working relationship with the contractor rather than a contentious one. When you get into the construction phase, if there's an issue that comes up, there's a little bit of accountability on both parties because they've all worked on the design prior to it being to construction. Another thing that came out of this is that our own project staff are, instrumental in enforcing that contract and making sure that we end up with a good project. And, just goes to show that regardless of where you are, you can still have a high quality project. One of the other lessons learned is that, we had assumed, certain things that the contractor wanted. So for instance, precast cap beams, we thought that that would be a great opportunity for the contractor. And, once they priced it out and looked at the risks with it, it turns out it wasn't a great option. So they went with the cast in place option anyway. So, sort of our underlying assumptions and biases are not always correct. And then real quick to end, so just recently there was a typhoon that came. This graphic on the bottom right will probably look familiar to those of you down in Florida in that region. And this typhoon, they've already come out and said that it's because of a warming ocean, and if the same storm were to have occurred in the 60s, it wouldn't have been near as powerful because the air would have been cooler. And so in the village of Kivalina, they were ready to evacuate. They were ordered to be ready, but they never ended up having to do it. It kind of went a little south. So Kivalina is up on this portion. Nome is down here. So as a quick aside, so this is a fairly new bridge in Nome that has the similar details to what Elmer was showing in the beginning, deck bulb tees and concrete filled steel pipe pile extensions. So this was a picture in August during our inspection. And then during that typhoon in September, you can see how much the sea level rose, and obviously there's a house that's impacting our bridge that shouldn't be there. And something interesting about this is that is actually the ocean that way. So this is storm surge pushing a building up into the bridge rather than the river pushing something down. So it's it just goes to show the power of the ocean. And with that, I think we'll open it up for the Q&A session.
All right, thank you, Elmer, and thank you, Nick. Certainly very challenging, very interesting bridge project, very informative. So at this point, we're going to turn it to Paul Lives to moderate the question and answer period. Paul?
Okay, Elmer and Nick, really an interesting project. We do have some questions that came in ahead of time, and then we do have some questions that have come in during the session, and they're continuing to come in. So let's go ahead and get in. The first question we have will be a design question. Then after that, most of them are construction. And the first one I have is this came in before the presentation. It says, does the design incorporate future erosion of the coastline?
So there's actually a good picture you're looking at here. So that entire causeway is armored along its length. And so in a local sense, there was design considerations for, what we normally expect, coastal erosion and scour. But as a global sea level rise, the logic was that the bridge is high enough already that if the water begins to inundate the causeway and the bridge, it has already inundated the village. And so there's no need for that causeway to exist because the village that it's serving is completely underwater.
Okay. Well, let's get over to some construction questions, and I've got two that came in. These also came in beforehand, and it revolves around your choice of the CMGC, Construction Manager General Contractor. First of all, why was the CMGC chosen for the project delivery method? You elaborated on that some. Do you want to add anything to that?
Yeah, I think in general, it allows us to get projects out quicker. When the contractor's on board from day one with the design, we can sort of tailor it to their needs and maybe get a jump one season ahead of when we normally would be able to if it were a standard design bid build project. So I think that was a big driver behind this. And because it's such a remote location, having a contractor on board to sort of buy off on our design decisions, helps head off some of those potential risks that could come down.
Okay. The second part to that was this question came in beforehand, and you mentioned potential risk. But how does CMGC reduce risk?
Yeah, so like an example for this is we sort of had the contractor look at different substructure or superstructure options, I should say. So if we assumed one thing and this went to a regular design build and we designed a type of girder, and then the contractor got on board and say, hey, there's no way I can ship that. You've designed something that I physically can't build. There needs to be a change order or some issue like that. And so having them on board, from the get-go, for instance, the additional field splice in there, they said, hey, we can only transport 100 feet segments. Okay, we'll add an extra field splice. Not that big a deal in design. Whereas if that came up during construction after it had already been bid and awarded, that could, you know, impact the schedule quite a bit.
Okay. Let's go on over to some other things. These are questions that came in. This one came in ahead of time and says, what was the method of pile installation? You may want to go look at your pile picture.
Yeah, so like I said, it was a pre-bore. So they pre-bored down and then they just used a regular impact hammer to get those piles into place. So I think they used a vibratory hammer to get them down to a certain depth, but we required a impact to verify capacity at the end.
Okay. Then there was a question here that came in about the piles, the connection. It says, was it a moment, or this one came in during your talk, was it a moment or a pin connection between the pipe piles and the pier cap? You've got that little gap in there.
Yeah, so this region in particular, so the cap beams are designed as capacity protected members, so they're designed to handle the full hinging capacity of the piles themselves. So it's, I guess, more of a moment connection, but the cap beams are designed to handle the full plastic moment, regardless of what the design forces could be.
Okay. Then there were a few questions that came in about temperature, and the first one was, what was the minimum temperature for placing concrete in the precast deck pockets around the shear connectors?
Yeah, it all goes back to that 40 degrees. So 40 degrees and rising, essentially, during the entire cure period. So that's for grout and Class A concrete and any sort of cast in place concrete.
Okay, and then it says which material was used. You said it was cast in place concrete for the cast in place in situ joints.
Yeah, that's just a normal prepackaged grout, so 9,000 psi, non-shrink, non-metallic, nothing special. You know, it's sort of meant to be, I'll say, as straightforward and easy as possible. So, you know, the only thing you have to do is add water to the correct ratio and mix it.
Okay, and then it said, see, what was the temperature? You said 40 degrees and rising. And the last part of this question was, and when were these joints cast? I guess there's two parts. I guess it was in the summertime.
Yeah, so I think most of the joint work was done in September. I think I had a date on there, so I would remember. Yeah, so September, and you know, temperatures just above that 40 degree point. There's a little bit of wind, obviously, and then we'll require like a wet cure. So I don't have any pictures of it, but you know, a burlap or something over there to keep those joints wet for, you know, the specified curing period.
Okay. And then they were poured when all the panels were set. Is that right?
Correct. Yeah, there's a contract requirement that they don't start grouting until all the panels are in place, and that allows, you know, the deflections to come in and you to set a true grade along there. So they'll set all those panels first and adjust them for height, and then they'll come back and start grouting them in.
I should mention, Paul, the contractor also had to have precautionary equipment on site to account for, you know, a sudden decrease in temperature that we didn't forecast. And so what's often used in Alaska is sort of a ground thaw hot water pipe hose system that they can spread under the thermal blankets or water cure system off the end of the bridge. That runs hot water across the whole bridge deck and kind of keeps the temperature up with thermal blankets on the top. So that material was on site and ready to go, but wasn't necessary because we didn't break that minimum temperature window.
Okay. We had a question that came in earlier, and this is maybe on your first picture where you showed the deck bulb tees. Elmer, that was in your presentation. It says, what do you use, see, for the deck bulb tee system, what do you use for ride quality on these? And the question, you seem to show an overlay on there. You show an asphalt overlay. That was the question.
Yeah, so most of them in, you know, urban areas will have an asphalt overlay. And so what's important there is that because you don't have a chance to do a cast in place deck to, you know, fix any issues, so there is a fit tolerance between these girders. So, you know, roughly 1/2 inch vertical difference is allowed at midspan, and I believe 1/4 inch at the ends of the girders, and then, you know, whatever little bit remains is usually taken up with the asphalt. But we do have a lot of locations where They're just driven on bare deck, so not an asphalt surface, and those are usually on more remote gravel roads.
Okay. And the question with that, it says, do you have any problems with skews causing misalignment of the girders?
It can become a challenge. This bridge in this picture is on like a 35-degree skew, if I remember correctly. And so, obviously at the ends, you end up with a little bit of differential. And so you're sort of looking for the best fit you can, recognizing that it's not going to be perfect, and you'll make up for it in that asphalt placement.
Okay, and then on the asphalt overlays, do you have any issues with delaminations and or spalling with the freeze thaw cycles up there?
I guess our extent of asphalt is usually pointing to it with an arrow and saying asphalt. I know we have some asphalt specialists in the state who, work on special designs that are, a denser, less porous mix that allows less water to penetrate. But I'll say in general, we don't generally have much of a problem with freeze thaw on our bridges and asphalt spalling.
Okay. Were there any, this one came in beforehand, were there any issues with transport of the precast deck panels to the site in terms of the condition upon when they arrived at the site?
I think on this project, there were a couple that got a little damaged, but for the most part, they came in pretty well. Like I said, they came on, if you imagine a 40-foot shipping container, but without the container part, just a flatbed with 4 posts on the ends. These came sitting nested inside of that and banded down. So, they're sort of a self-contained unit. We have had issues on other projects where they get banged up, especially, an operation like this where they're sort of, loading them in a factory and then, unloading them onto a barge and then moving them multiple times. So there's lots of different opportunities for them to get damaged. But in general, because they're just regular reinforced concrete, the repairs are not too extraneous. There's no pre-stressing stands that could get damaged or post-tension ducts or those sorts of things. So.
Okay. There was a question here regarding the precast panels, and it says, I guess you do not have to worry about when the web is plumbed. This is for the steel girders. You can plumb them either with just the dead load of the girder, or you can plumb them with the dead load when the panels are on them. I don't know which method y'all use. Could you elaborate on that any?
Yeah, and because those leveling screws are independent on each girder, if the girders don't sit, exactly plumb and level with each other, there's an opportunity to, adjust them independently. And because that crown is cast in, these abutments are actually level. There's not a stepped abutment. All of the cross slope is taken care of in these deck panels. So the girders all sit at the same elevation, if that makes sense.
Okay. And they're all plumb. I mean, a 90-degree bridge.
Yeah, correct.
So yeah.
Correct. Yeah,
I think that's pretty good. Okay. And there was a question that came in beforehand about what was the biggest challenge for such cold weather?
I'm sure just working in it in general, your production rates slow down, equipment has to be warmed up and kept running. A lot of times on these remote sites where it's really cold, the pieces of equipment will run 24 hours a day because it's such an issue. If they shut down, your engines can start to freeze over and those sorts of things. And so, just the general working conditions and getting equipment and contractors on site. You saw that runway, so they're coming in on 4 or 5 person planes. And then those contractors and laborers are, sort of living in this Arctic wilderness almost for, many months at a time. So I think just the general working in the cold. I don't think there were any specific issues. Most of our contractors are pretty well versed at working in cold weather. So, cold weather concrete is not an unheard item for them. It's pretty much a standard practice at the beginning and the ends of our construction season.
Okay. There was a question that came in beforehand about the lessons. What were the lessons learned for this project? You've kind of covered that. You want to add anything to that at all?
I think that's mostly what we got out of it. I mean, we're kind of happy. So there weren't many negative lessons learned. We were kind of scratching our heads yesterday saying, did we learn to change anything? There's the standard construction issues of, we thought we knew what the erection plan was going to be, but we didn't have, the exact numbers for it until the girders were on site and sort of surveyed in once they were fully bolted up. But I think that's, pretty part and parcel for any project. So I think overall we were pretty happy with it. And if anything, the lesson learned was that this system worked. Not only the structural system on the bridge, but the CMGC process. And we think we ended up with a pretty nice product out there.
Okay. It's about 2 o'clock, and we've got a lot of questions that have come in during the question and answer session. So I'm going to get Don Digamon to come in and pick it up now, and he will go ahead and ask the rest of it. Don?
Thanks, Paul. First question that came in during the presentation, what do you expect the life of the bridge to be, and what type of maintenance will be performed?
Yeah, so maintenance, as I mentioned, is going to be pretty minimal. There might be one person in town who's in charge of clearing the runway, but that's sort of a seasonal job, and so there's definitely not specialty maintenance going out there on a regular basis. The design life is just the standard AASHTO 75-year design life. In this particular case, it'll be interesting to see if the sea level rise necessitates that bridge, or it makes that bridge pointless for being there. If you get my meaning, if the sea level rise happens faster and inundates the village, and that village has to be completely abandoned prior to us reaching that 75-year design life.
Okay. Question about the transverse keyways. Were the unreinforced transverse keyways between the precast deck panels designed to resist differential deflections under HL93 truck moving across?
So I'll give my answer, and then maybe Elmer will step in. So we've traditionally designed these bridges to act non-composite because there's not continuous reinforcing across for service limit states. At the strength limit state, we assume that those keyways, any shrinkage cracks in that transverse grout will close up, and you'll be able to transfer force through there. So I think, yes, they are designed, maybe not explicitly, to handle those differential deflections between panels. And because there's a fully, grouted haunch underneath, in that regard, they're going to act more or less like a cast-in-place deck.
And I'll add a little bit that we've been using these precast deck planks predominantly as replacement for timber decks that were used, I'll say in the 70s and 80s. The biggest application we used is on what we call the Dalton Highway that goes from Fairbanks, Alaska to Prudhoe Bay, the main oil route. It's an industrial route with a heavy 80 TT, and these same panels have performed well on a heavily loaded heavy industrial route. So we're really not worried about them on a remote village route where probably the heaviest piece of equipment, like Nick mentioned, is a grader, maybe the construction equipment that built the bridge. But after that, there are perhaps small pickup trucks and four-wheelers, ATVs, we call them. So pretty light loads. But we have had good success with this detail on, I don't know what percentage of bridges have them, but maybe 5% of our bridges and most of the bridges on this Dalton Highway. So I suppose anecdotal evidence that they perform well.
I'll go back to this. There's a question that kind of repeated from a previous question, but lifespan expected of the bridge.
Yeah, I think just the same, that, design with that standard 75-year design line in life.
Okay. A couple questions about the pile connections. You talk about plastic hinge at the junction between the pile and the pile cap due to the size of the structure, limited mass, and structure not stiff. Was it necessary to consider the hinging instead of performing an elastic design of the structure?
So there was a lot of words in there, but I think I'll essentially go back and say that the cap beams are designed for the full overstrength plastic hinging of that pile section without the shell on it, and that's why we create that gap in there. So we essentially are forcing that hinge to form, and then the cap beam is designed to take that entire overstrength plastic hinging force, and that's in accordance with the AASHTO design or guide specifications for LRFD seismic bridge design.
Yeah, I'll add a little bit there as well, Don. We do design that gap region to accommodate traditional lateral loads, lateral earth pressure, live load surcharge, those types of issues for both strength and service limit states. That defines the amount of reinforcing steel inside the pile itself. But we then design pretty much every bridge throughout the state for capacity or following the capacity protection principles. So even though the design of the reinforcing steel might come from other lateral loads, the plastic hinging forces, the overstrength plastic hinging forces, are those loads that are governing the design of the cap beam and up, if that makes any sense. So we want, and maybe this is a nod to the future. There's a push for resiliency, redundancy, ductility, robustness of the system. Even though this site doesn't have a particularly high seismic demand, the detailing is what we're really talking about here. We're providing confinement of that gap region, which is fairly well confined, as it's only a 2-inch gap between a steel pipe and a concrete cap. But designing it to accommodate large plastic rotations and deformations that can come out of that, regardless of the source of those deformations. Again, at this site, probably not seismic, but if there were a large coastal storm that exceeded expectations and washed away the abutment approach fill, and these piles at the abutments had to act like piers resisting ice loads or storm surge loads, they would be able to accommodate those with a large ductile capacity, minimizing the threat of collapse, for example. So I don't know if that's the clear answer that we're looking for, but I guess I'll say that the reinforcing steel is designed for sort of non-seismic considerations. Then the seismic considerations of plastic hinging is followed through the system.
Understood. In line with that, and I believe you might have answered this question with your previous or parts of it. Does Alaska allow pile in-ground hinging? If not, what is Alaska's strategy for capacity protecting the bent cap where in-ground hinging may not occur during a design earthquake?
Why don't you just finish your thought, Elmer, since you're already...
I'll finish my thought. Yes, Alaska allows below ground or in-ground hinging. So for that pier pile on slide 3 or 4, Nick, if you want to go back to the pier. So for an abutment, a single span bridge, we do design for these seismic forces, but this pier that you're looking at on the screen, this is our sort of bread and butter. Yes, in the longitudinal direction, we essentially have a pinned connection at the cap beam to the superstructure, but in the transverse direction, we've got fixity at the gap region, the top of the pile. In both cases, plastic hinging may form below the ground line. Now that stated, working with researchers and now incorporated into the performance-based seismic design guidelines, we have strain limits that define certain performance objectives of that concrete-filled pipe. So one of those is the onset of pipe wall buckling. So that's typically speaking a threshold for which we don't want to exceed the below ground response. That might be an inelastic response, but it's hard, you really can't much inspect inelastic response by itself, but you can see pipe wall buckling. So by limiting our below ground predicted response or demand, if you will, to this onset of pipe wall buckling, we wouldn't anticipate any below ground damage of any real consequence. That said, we can continue our plastic hinge rotations beyond that onset of buckling all the way to pipe wall rupture or fracture, and that's a very significant amount of deformation associated with that. I'll try to put some guide rails on it. If we had a conventional reinforced concrete column, perhaps we would be good seismically for 1/4 to 1/2 of that column's diameter for seismic deformation capacity, in that range. For these concrete filled pipe walls, yielding might be 1/2 or so of the pipe wall diameter, or the pipe diameter, sorry, and ultimate might be a full pipe diameter or more. It measured in feet as opposed to inches. Now, what does that mean for the planet around us? If we have a pier that can accommodate 4 feet of lateral deformation, chances are we've got bigger problems, right? We are anticipating no collapse of the bridge, but if you had 4 feet of movement, very likely there's extensive liquefaction, your road is gone, probably your buildings and houses around it are toast. So I think we've got a system that's quite reliable, robust, and so forth. And it's designed to, again, it's not just seismic. These are detailing features that we can take advantage of for other lateral loads that are unanticipated. If, Nick, you could go to the Snake River Bridge in Nome, that bridge, again, in a relatively low seismic hazard zone by Alaska standards, is designed with those same characteristics and same features. We never envisioned a building load, a lateral load of a building on the bridge. It wasn't part of our plan. But I assure you, even if that load would have been more significant, I'm confident in the reliability of the system that even if we'd have deformed the piers plastically, it wouldn't have led to a collapse. Everything's glued together, if you get my meaning. All the superstructure components are connected to rigid diaphragms, to the cap beam, to the piles, and that system could have deformed laterally 3, 4, 5 feet before we got to something where we start fracturing bars and so forth. So we think, for us in Alaska, that's the way we do business. It might be that's something that folks want to think about in the future as we look towards this reliability and ductility and so forth, as who knows what the next storm surge is bringing. Well, it used to be a 100-year flood, seems to be the 10-year flood. It just happens all in fact, this September storm event was followed 3 weeks later by another high water event, lesser, but still 3 weeks later, another very significant event.
Well, excellent response there. Going into abutment details. Curious about bearing configuration. It almost looks like a semi-integral abutment. How does extreme cold impact the functionality of the bearing movement?
Yeah, correct. So it is a, I guess, semi-integral, and so it's, there's still a separation between the cap beam, which the piles are connected to down here, and the superstructure. It is a consideration. Our temperature swings are obviously, pretty large, and generally our bridges are built in the summer when it's the warmest, and so they're not, nicely built in the middle of that temperature range. They're generally built at the one extreme end, generally speaking, at the warm end. And so I forget what the anticipated thermal movements were on this, but it's 190 feet, so it's probably not massive. And it was enough that we could handle it with just the back wall deformation and using the regular elastomeric bearing pads.
Okay. Can you provide highlights on the special design considerations, included in the design for deck panels, precast girders, and columns?
Yeah, so there were no precast columns here. The deck panels are essentially designed per LRFD, but that strip width is obviously limited to the panel width, and so the panels are designed, as if they were a freestanding unit there. And so, for instance, these panels are, almost 5 feet wide, and so it's designed for that total limit. Obviously, the reinforcing has to avoid all these holes that we've put in it, and so there's a little bit of legwork to get those in, but other than that, it's essentially a standard LRFD deck design, just broken up into chunks.
Okay, that's we got 3 minutes left. Oh,
I was going to say, I'd add, I don't think it governed. I was trying to look through the calcs, but we also have to consider that shipping, picking, bunking, that you wouldn't normally look at, obviously, with the cast in place deck, but that can be a controlling consideration. So, we try to set those lifting anchor points at reasonable locations to try to minimize those, let's call them non-installed load configurations.
Great answer. A couple minutes left, so I'll wind down here. Couple more questions. Were the bridge railings cast in place?
They were, yeah. So those curbs are sort of the last item that is cast in place. Yeah, so they were cast in place and the rails just normally assembled on. So this portion is a cast in place on top, and that helps if there's any unevenness in the panels to make sure that the railing and the curb end up with a nice true line that you see as you're driving across it.
Okay, got the time, probably one or two more questions. I saw you were able to control the air temperature during concrete placement. What about the temperature of the surrounding ground?
Yeah, and so generally there's also a requirement in the contract that ground be brought up to temperature as well. Same thing with the forms and the rebar, so you can't place, warm concrete into a frozen form with frozen rebar and ice crystals and those sorts of things. And ironically, sometimes the problem is we heat the ground too much, and since it's all based on permafrost and ice, we can unintentionally thaw that ground that everything's sitting on. So putting heat into there, but not putting in so much heat that you start to cause adverse problems is important.
Okay. And last but not least, not actually a question, just says, great job, beautiful work. And Lou, I'll hand it back to you.
All right. Okay. Thank you, Don. Thanks, Nick and Elmer. Very interesting and challenging project. So on that note, we are going to end our webinar today. We look forward to see many of you in Miami, Florida for the 2022 International ABC Conference. Okay, so long.